The night of June 14th, 1943, and Squadron Leader Bob Braham sits in the cockpit of his de Havilland Mosquito night fighter at RAF Westmoreling, watching his newly installed equipment with a mixture of hope and skepticism. The device before him, a radar receiver with the codename Serate, represents something that conventional wisdom says shouldn't work, something that breaks every rule about how radar detection is supposed to function. Within hours, this forbidden radio hack will allow him to hunt German night fighters using their own radar emissions, turning the hunters into the hunted, in a reversal of fortune that will fundamentally alter the night battle over Europe. What Braham cannot know, as he waits for the order to take off, is that this single piece of equipment will evolve into a family of radio hacking devices that will give Allied pilots an almost supernatural ability to locate enemy aircraft, reading the Luftwaffe's Playbook by exploiting the very systems designed to give German pilots an advantage. The story begins not with Serate, but with the German Liechtenstein radar, a technological achievement that had given the Luftwaffe a decisive edge in the night battle over Germany since 1942. Hauptmann Ludwig Becker had scored the first Liechtenstein-aided victory in August 1942, and by early 1943, German night fighters equipped with this radar were decimating RAF bomber streams, shooting down hundreds of Lancasters and Halifaxes as they lumbered toward their targets deep in the Reich. The Liechtenstein BC system, operating at frequencies between 420 and 480 MHz, allowed German pilots to detect British bombers at ranges up to 4 kilometers, giving them plenty of time to maneuver into firing positions before the bomber crews even knew they were under attack. The system used a distinctive antenna array nicknamed the Matratze, or mattress, by German pilots, an ungainly collection of dipole aerials protruding from the nose of Messerschmitt 100s and 10s and Junkers 80s that looked like a bed frame strapped to the aircraft, but proved devastatingly effective in the darkness over Europe. German night fighter pilots had developed a methodical system for prosecuting their attacks, vectored toward the bomber stream by ground controllers using Freya and Würzburg radars, then switching to their own Liechtenstein sets to complete the interception. Oberleutnant Heinz Wolfgang Schnaufer, who would become the highest-scoring night fighter pilot of the war with 121 victories, described the process as almost surgical in its precision, the Liechtenstein scope showing the target as a bright blip that grew larger as the fighter closed to firing range, allowing the pilot to position his aircraft perfectly below and behind the bomber before opening fire with upward-firing cannons. The system worked so well that by March 1943, RAF Bomber Command was losing an average of 5% of aircraft dispatched on each mission, an unsustainable rate that threatened to end the strategic bombing campaign altogether. Air Marshal Arthur Harris, Commander-in-Chief of Bomber Command, desperately needed a solution to the night fighter problem, something that could tip the balance back in favour of his bombers. The solution came from an unlikely source, the recognition that German radar was not just the detection device, but also a radio transmitter that could be detected and tracked by Allied equipment. Dr. Robert Coburn at the Telecommunications Research Establishment at Malvern understood that every time a Liechtenstein radar transmitted its search pulse, it was broadcasting its location to anyone with a receiver tuned to the right frequency. The concept was simple but revolutionary. Instead of trying to jam or confuse the German radar, why not use it as a homing beacon, allowing RAF night fighters to find and destroy the Luftwaffe fighters before they could attack the bomber stream? The idea was proposed in early 1943 by Wing Commander Edward Addison, who commanded 85 Squadron and had been frustrated by the difficulty of finding German night fighters in the vast darkness over Europe. Addison reasoned that if RAF fighters could detect Liechtenstein emissions, they could turn the tables on the Germans, hunting them the way German fighters hunted British bombers. The Air Interception Committee approved the proposal for research into what they called a Homer radar on April 3, 1943, and TRE at Malvern was tasked with developing a working system. The engineers there faced a unique challenge. They needed to create a receiver sensitive enough to detect relatively weak Liechtenstein emissions at useful ranges, but selective enough to distinguish between different German fighters and provide directional information to guide the pilot toward his target. The frequency range of 420 to 480 MHz presented particular difficulties because it required specialized components that were not commonly available, and the receiver had to be packaged in a form that could fit into already cramped RAF night fighters. The breakthrough came when engineers realized they could modify the existing AI Mark IV radar receiver, which operated at a wavelength of 5 meters or 200 MHz, to detect the 75 centimeter wavelengths used by Liechtenstein. The antenna array of the Mark IV was actually almost perfectly suited to pick up Liechtenstein transmissions, a fortunate coincidence that dramatically accelerated development. The timing of the development proved remarkably fortunate because on May 9, 1943, just weeks after the Sarate project began, a crew from the Luftwaffe's 4th Night Fighter Wing defected to Britain, flying their fully equipped Junkers 88R1 Night Fighter to RAF Dice in Scotland. The aircraft, coded D5+EV, carried a complete Liechtenstein BC radar system that TRE engineers could examine in detail for the first time. Flight Lieutenant H.J. Jackson, a German-speaking RAF officer, flew with the defecting crew and provided detailed information about how the Liechtenstein operated, its frequencies, its power output, its antenna patterns, everything the British needed to optimize Sarate for maximum effectiveness. This intelligence windfall allowed TRE to refine their design dramatically, knowing exactly what signals they needed to detect and how strong those signals would be at various ranges. The engineers worked around the clock, understanding that every day's delay meant more bombers shot down over Germany. By early June 1943, the first Sarate units were ready for operational testing, and 141 Squadron under Bob Braham was selected to pioneer the new equipment. Braham was already a legendary figure in the RAF, having scored 26 victories including 3 in a single night, and his tactical expertise combined with his willingness to experiment with new equipment made him the ideal choice to lead the Sarate trials. The equipment installed in his Mosquito consisted of a receiver tuned to Liechtenstein frequencies, connected to a cathode ray display that showed the direction and approximate strength of any detected emissions. The operator, sitting in the seat behind Braham, would watch the scope for the characteristic pulse pattern of Liechtenstein radar and call out directions to guide Braham toward the German fighter, close enough for the Mosquito's own AI Mark IV radar to pick up the target for the final approach and attack. The first operational Sarate mission took place on the night of June 14, 1943, when 141 Squadron's Mosquitoes accompanied a bomber raid to Oberhausen. Braham and his radar operator, Flight Lieutenant William Gregory, detected their first Liechtenstein emissions at a range of 100 miles, an astonishing distance that neither man had expected. Gregory watched the scope as the signal strength increased, calling corrections to Braham, who manoeuvred the Mosquito toward the unseen German fighter somewhere in the darkness ahead. The technique required extraordinary patience and discipline, because following Sarate contact meant extended pursuits, sometimes lasting 20 minutes or more, following a manoeuvring target through hostile airspace while trying to avoid detection. At 15 miles range, the Sarate signal became strong enough to provide accurate directional information, and Gregory guided Braham into a pursuit curve, closing the distance while trying to approach from the German fighter's blind spots. At 4 miles, the Mosquito's AI Mark IV radar acquired the German aircraft, showing it as a distinct blip on the scope, allowing Braham to complete the final approach visually. What Braham saw through his windscreen was a Messerschmitt 110 night fighter, its Matratza antenna array clearly visible in the moonlight, the German crew completely unaware they were being stalked. The German aircraft was heading toward the bomber stream, its pilot concentrating on his own Liechtenstein scope, looking for British bombers to attack. Never imagining that his radar was betraying his position to an RAF fighter, Braham closed to 400 feet, positioning his Mosquito slightly below and behind the Messerschmitt, in a mirror image of the German tactics used against bombers. And when his gun sight settled on the enemy aircraft, he fired a burst of 20mm cannon rounds that tore into the Messerschmitt's fuselage. The German aircraft exploded in a ball of fire that lit up the night sky, the crew having no chance to evade or even understand what had happened. Their Liechtenstein radar, the very tool that made them lethal hunters of British bombers, had become a beacon, guiding an RAF fighter to their destruction. Braham scored 3 more Sarate-assisted victories that summer, proving the system's effectiveness beyond any doubt. Other crews in 141 Squadron reported similar successes, finding that Sarate gave them an enormous tactical advantage over German fighters who had no idea they were being hunted. The psychological impact on Luftwaffe night fighter crews proved as significant as the physical losses, because German pilots began to realize that their radar emissions were being detected, that the darkness that had protected them was no longer absolute. Hauptmann Heinz Rocker of Night Fighter Wing 2 described a growing paranoia among his pilots, knowing that turning on their Liechtenstein radar might be signing their own death warrant, but being unable to fight effectively without it. The Luftwaffe was caught in an impossible bind. They needed radar to find British bombers, but using radar made them vulnerable to Sarate-equipped Mosquitoes. The German response to Sarate came too late and proved largely ineffective. The Luftwaffe developed a radar warning receiver called Naxos ZR that could detect British AI radar transmissions, allowing German pilots to know when they were being tracked, but this only confirmed they were under attack without providing much help in evading. Some crews tried turning off their Liechtenstein radars periodically to break the serrate lock, but this meant losing their own ability to find bombers, effectively neutralizing them as threats. The Luftwaffe also attempted to introduce a new version of Liechtenstein, the ww2 operating at lower frequencies around 90 MHz, where existing serrate equipment could not detect it, but this countermeasure would not become widely available until 1944, giving the RAF nearly a year of serrate dominance. As successful as serrate proved to be, it represented only the first step in the Allied program to exploit German radio emissions. The next breakthrough came with a device called Perfectos, developed in early 1944, that took radio hacking to an entirely new level by turning the Luftwaffe's own identification friend or foe system against them. The IFF concept had been developed independently by both sides during the war as a way to distinguish friendly aircraft from enemy aircraft on radar screens. The German system, designated FUG-25A Erstling, worked by having a transponder in each aircraft that would automatically respond to interrogation signals from friendly ground radars, sending back a coded pulse that would appear as a distinctive blip on the radar operator's scope, confirming the aircraft was German. The system had been in use since 1941 and was installed in virtually every Luftwaffe aircraft by 1944, an essential safety device that prevented friendly fire incidents and allowed ground controllers to track their own fighters. British intelligence had learned about the FUG-25, a system through various sources, including captured equipment and interrogation of prisoners, and engineers at TRE realised the system's potential vulnerability. The FUG-25A operated on specific frequencies, around 125 MHz, and would respond automatically to interrogation signals without any action required by the aircraft crew. A design feature meant to reduce pilot workload, but which also meant the transponder could be triggered by enemy signals. TRE engineers began work on a device that would send out false interrogation signals, mimicking those from German ground radars, causing nearby Luftwaffe aircraft to transmit their IFF responses, which could then be detected and used for homing. The concept was breathtakingly simple in theory, but challenging in practice because the interrogation signal had to be precisely formatted to trigger the FUG-25A, and the receiver had to be sensitive enough to detect the relatively weak IFF responses at useful ranges. The development of Perfectos progressed rapidly through early 1944, aided by the capture of additional German equipment and the interrogation of Luftwaffe personnel who provided detailed information about how the FUG-25A system operated. By summer 1944, the first Perfectos units were ready for installation in RAF Mosquitoes, giving these aircraft an additional tool for finding German fighters. The device consisted of an interrogator that sent out triggering pulses at regular intervals and a receiver that detected any FUG-25A responses, displaying them on a scope similar to that used for Surrat. Unlike Surrat, which only worked against German fighters that had their Liechtenstein radar turned on, Perfectos could detect any German aircraft with an IFF transponder, whether they were fighters, bombers, or transport aircraft, and the transponder was almost always active because turning it off meant the aircraft would appear as hostile to German defences. The first operational use of Perfectos occurred in June 1944, coinciding with the Normandy invasion, when Mosquito crews found they could detect German aircraft attempting to attack Allied shipping in the Channel. Flight Lieutenant Douglas Palmer of 85 Squadron described the revelation of seeing his Perfectos scope light up with IFF responses from German fighters that were completely unaware they were broadcasting their positions. Palmer and his navigator, Flying Officer Jack Forshaw, followed a Perfectos contact for several minutes before acquiring the target on their AI radar, closing to visual range to find a Junkers 88 night fighter, its crew oblivious to the fact they were being hunted. Palmer fired a single burst that set the Junkers port engine ablaze, forcing the crew to bail out over occupied France. The German pilot, taken prisoner after the war, expressed shock when told his own IFF system had betrayed him, having assumed the British had somehow acquired a German radar set and were impersonating ground controllers. The combination of Serrate and Perfectos gave RAF night fighter crews an unprecedented ability to locate German aircraft in the darkness over Europe, effectively giving them a form of electronic vision that their opponents lacked. Wing Commander Bob Braham, who had pioneered Serrate, later received a Perfectos-equipped Mosquito and described having two ways to find the enemy as being like hunting with both a dog and a spotlight, the Serrate showing fighters with their radar on and the Perfectos showing everyone else. Crews learned to use both systems together, watching their scopes for any electronic emissions that might lead them to a target, then using their AI radar for the final approach. The effectiveness of these systems forced fundamental changes in German tactics, with night fighter crews increasingly reluctant to use their radar or IFF systems, reducing their effectiveness against the bomber stream. The Luftwaffe's attempts to counter perfectos proved more successful than their efforts against Surratt, because the countermeasure was relatively simple: turn off the FUG-25, a transponder. By late 1944, German night fighter crews were routinely flying with their IFF systems disabled, accepting the risk of being shot at by their own defences, rather than advertising their positions to RAF night fighters. This countermeasure significantly reduced perfecto's effectiveness, though it never completely eliminated it, because some German crews forgot to turn off their IFF, or turned it on briefly to identify themselves to ground controllers, giving alert RAF crews a window to detect them. The psychological pressure of knowing that simply having safety equipment turned on could result in being attacked added another layer of stress to German night fighter operations, contributing to the overall degradation of Luftwaffe effectiveness in the night battle. The impact of Surratt and perfectos on the strategic bombing campaign cannot be overstated, because these devices, combined with other electronic warfare equipment and tactical improvements, helped turn the night battle decisively in favour of the Allies by late 1944. German night fighter losses increased dramatically, not just from direct Surratt attacks, but also because Luftwaffe crews became more cautious, less aggressive in pursuing bombers, knowing they might be stalked by RAF night fighters. The percentage of bombers lost per mission decreased from over 5% in early 1943 to below 2% by late 1944, a reduction that made the difference between an unsustainable campaign and a decisive strategic advantage. Every German night fighter shot down by a Surratt-equipped Mosquito meant dozens of bombers that survived to attack their targets. And every German pilot, made cautious by fear of radio detection, was a pilot whose effectiveness was compromised. The technical sophistication of both Surratt and perfectos impressed even the Germans when they finally understood the full extent of what had been done to them. General Major Josef Kammhuber, who had built the German night fighter force, stated after the war that the British electronic warfare capabilities had been far more advanced than German intelligence had estimated, and that the exploitation of Liechtenstein and Fuji-25A emissions represented some of the most innovative thinking in the entire air war. The concept of turning an enemy's own systems against them, of using their technology as a weapon for their destruction, became a fundamental principle of electronic warfare that remains relevant to this day. Modern military forces still seek to exploit enemy emissions, though the specific technologies have evolved, from radar to include radio communications, data links, and even electromagnetic signatures from electronic equipment. The crews who flew Surratt and perfectos missions faced unique dangers because their tactics required them to operate alone, away from the main bomber stream, stalking German fighters through hostile airspace, where a moment's inattention could prove fatal. These men developed a particular kind of aerial combat, patient and methodical rather than the furious dogfighting of day fighters, following electronic contacts through the darkness for 20 or 30 minutes, maintaining perfect concentration while knowing their target might suddenly become aware of them. Flight Lieutenant Ronnie Walker of 141 Squadron described the tension of following a Surratt contact, watching the signal strength increase on his scope, knowing that at any moment the German crew might spot his Mosquito, or that another German fighter might stumble across him. The successful Surratt crews were those who could maintain that concentration night after night, developing an almost intuitive sense of how German fighters manoeuvred and where they were likely to be found. Bob Braham's career exemplifies the impact individual pilots could have using these electronic warfare tools, as he would ultimately be credited with 29 confirmed victories, many of them achieved using Surratt and later perfectos to locate his targets. His success inspired other pilots and helped prove that radio hacking was not just a theoretical advantage, but a practical tool that could produce tangible results in combat. Braham's techniques, refined through experience and shared with other crews through training and debriefings, became standard operating procedures for Royal Air Force night fighter squadrons, creating a body of tactical knowledge that made the equipment increasingly effective as more pilots learned to exploit it. The Germans never developed an effective counter to these tactics, because doing so would have required them to stop using radar and IFF altogether, essentially forcing their night fighters to operate blind, which was not a practical solution. The story of Surratt and perfectos represents more than just the tale of two devices. It illustrates the nature of technological warfare, where advantage comes not just from inventing new systems, but from understanding and exploiting the enemy's systems. The British did not defeat German night fighters by building better radar or more powerful aircraft, though those things helped, but by recognizing that German technology created vulnerabilities that could be exploited. The engineers at TRE, working in relative obscurity at Malvern, achieved strategic results through clever application of radio theory, understanding that detection is a two-way street and that any transmitter is also a beacon. This principle, that an enemy's technology can be turned against them, became a cornerstone of modern electronic warfare, visible in every conflict since World War II, where signals intelligence and electronic countermeasures play crucial roles. The German experience with Seraten Perfectos also demonstrates the danger of complacency in military technology, as the Luftwaffe had deployed Liechtenstein and Fuji 25A without adequately considering how those systems might be exploited by an enemy. German engineers understood that radar emissions could be detected, but assumed the difficulty of building effective homing receivers would prevent the British from doing so, an assumption that proved catastrophically wrong. Similarly, the Fuji 25A was designed with security in mind, using coded responses that German engineers believed would prevent exploitation, but they failed to consider that the British might simply trigger the system and use the responses for direction finding, without caring about the actual codes. These oversights stemmed from a fundamental underestimation of British technical capabilities, a mistake that cost the Luftwaffe dearly as the war progressed. The legacy of these forbidden radio hacks extends far beyond their immediate tactical success, because they established principles and techniques that remain relevant in modern warfare. The concept of exploiting enemy emissions is now standard practice for all military forces, with entire branches of the military dedicated to signals intelligence and electronic warfare. Modern aircraft carry sophisticated warning receivers that alert pilots when they are being tracked by enemy radar, descendants of the same concept that motivated Seraten Perfectos. The evolution from those early devices to modern systems represents continuous refinement of the same basic idea that the electromagnetic spectrum is a battlefield where detecting and exploiting enemy signals provides decisive advantages. Every radar warning receiver, every electronic support measures system, every signals intelligence platform in use today owes something to the pioneering work done at TRE in developing Seraten and Perfectos. The human element in this story deserves emphasis, because the success of these systems depended not just on clever engineering, but on brave men willing to fly into hostile airspace, relying on untested equipment to find and destroy enemy fighters. The radar operators who sat behind pilots like Bob Braham, watching their scopes through long hours of darkness, calling out directions while knowing their lives depended on the pilot's skill and the equipment's reliability, deserve recognition as true pioneers of electronic warfare. These men operated at the intersection of technology and courage, using tools that no one had used before to fight a new kind of battle, and their success helped secure Allied victory in the night skies over Europe. The story ends not with a single dramatic moment, but with the gradual erosion of German night fighter effectiveness, as Seraten and Perfectos, combined with other Allied advantages, made the night battle increasingly one-sided. By early 1945, RAF Bomber Command was operating almost with impunity over Germany. The once fearsome night fighter force reduced to scattered remnants, its pilots demoralized by constant losses and the knowledge that their own equipment betrayed them. The forbidden radio hack that Bob Braham had tested in June 1943 had evolved into a comprehensive electronic warfare system that gave the Allies the plat to read the enemy's playbook, knowing where German fighters were before the Germans knew Allied night fighters were hunting them. The 8 black holes in the nose of a B-25 Mitchell had terrorized Japanese shipping in the Pacific, but the invisible electronic emissions that Seraten Perfectos detected proved equally deadly to German night fighters over Europe. Different weapons in different theatres, but both representing the Allied talent for innovation and the willingness to break conventional rules in pursuit of victory.